Hello everyone, welcome to this session. In this session, we will be concentrating on one important method of estimation called method of moments. It is a method for estimation of population parameters based on moments, and this method is developed based on one important law in statistics called law of large numbers. The law of large numbers states that if sequence xn independent and identically distributed random variables with common mean mu and variance of xi sigma square which is less than infinity, then the sequence xn bar converges to mu the population mean in probability as n tends to infinity. Also we consider the definition of consistent estimators. It is interesting to see that an estimated Tn is consistent for theta if Tn converges to theta in probability. Hence, let x1, x2, etc. xn is a random sample from the population with density function f of x comma theta. If expectation of xi is equal to mu of theta, a function of theta, then x bar converges in probability to mu of theta and x bar is consistent for mu of theta. If mu inverse exists and is continuous, then mu inverse x bar converges in probability to mu inverse mu of theta which is equal to theta, and hence mu inverse x bar is consistent for theta. This is used using the weak law of large numbers and the definition of consistent estimators. This is the basic idea of method of moments, and solving the moment equation we get consistent estimators. To make it more clear, let us discuss about the population and sample moments. Suppose we have x, a random variable x following distribution with probability density function f of x comma theta. Then we know that the first order moment expectation of x can be calculated using the formula integral over x f of x theta dx if f of x comma theta is a continuous distribution. Otherwise, in the place of integral you have to use summation symbol. Let us denote this as mu 1 dash. Now, the second order moment expectation of x square is equal to integral over x square f of x comma theta dx, and let us denote it as mu 2 dash etc. up to the kth order moment expectation of x raised to k is equal to integral x raised to k f of x comma theta dx is equal to mu k dash. These are the population moments, and these population moments may be functions of the population parameters. For example, when you have a random variable x following Poisson distribution with the parameter lambda, then the first order moment mu 1 dash is equal to lambda, the second order moment mu 2 dash is equal to lambda square plus lambda. So, these are functions of the parameter lambda. Similarly, in the case of normal distribution n mu sigma square, we have the first order moment mu 1 dash is equal to mu, and the second order moment mu 2 dash is equal to sigma square plus mu square. Here we have two parameters mu and sigma, and the population parameters are the population moments are functions of the population parameters. Now, let us consider the sample moments. If you are taking a random sample from the same population with the density function f of x comma theta, then the first order sample moment is summation I is equal to 1 to n xi divided by n. Let us denote this as m1. The second order sample moment is calculated as summation I is equal to 1 to n xi square divided by n. We denote it using m2 etc. up to the kth order moment, sample moment, summation I is equal to 1 to n xi to the power k divided by n, and that is equal to mk. So, these are functions of the sample values. In the method of moments, we equate these sample moments with the population moments, and the estimators for the parameters are obtained by solving the system of these equations. So, it means that we will equate the first order population moment mu 1 dash with the first order sample moment m1, second order population moment mu 2 dash with the second order sample moment m2 etc. The kth order population moment mu k dash with the kth order sample moment mk. So, solving these equations, we will get the moment estimators of the parameters. If we have only one parameter to be estimated, we need only one equation, and equating the first order moment may be enough. That is the sample mean with the population mean. If we have two parameters to be estimated, we need two equations, and equating the first and second order moments with the corresponding population moments may be enough for the estimation purpose. There are situations where this rule cannot be followed, examples for which we will see in this session itself. Let us consider some examples. You consider a random sample from the Poisson distribution. We know that the density function of the Poisson distribution is p of x comma lambda is equal to e raised to minus lambda, lambda raised to x by x factorial when x is equal to 0, 1 etc. We have only one parameter lambda here, and the first order population moment expectation of x or mu 1 dash is equal to lambda. Since we have only one parameter lambda, we can equate this first order population moment with the first order sample moment. So, we get lambda is equal to the first order sample moment summation I is equal to 1 to n xi divided by n, and we know that this is equal to x bar. Hence, the moment estimator for the parameter lambda, let us denote using lambda curl, and this is equal to x bar. So, in the case of population or in the case of Poisson distribution, the moment estimator of the parameter lambda is x bar. Now, let us consider the exponential distribution. The exponential distribution is having density function f of, let us consider the parameter as lambda, f of x comma lambda is equal to lambda e raised to minus lambda x, where x is greater than 0. Then the first order population moment or the mean is mu 1 dash is equal to 1 by lambda. Here also we have only one parameter lambda. Equating this with the first order sample moment, we get 1 by lambda is equal to summation I is equal to 1 to n xi divided by n, and that is equal to x bar. So, it means that lambda is equal to 1 by x bar, or we can consider or we can take the moment estimator of the parameter as lambda curl is equal to 1 by x bar. Now, let us consider another example involving two parameters. So, we are taking a random sample from the binomial distribution with parameters n, capital N and small p. So, the probability mass function is probability of x is equal to small x is equal to NCx p raised to x 1 minus p raised to n minus x, where x is equal to 0, 1, 2 etc. up to capital N. Here also we know the first order population moment and the second order population moment. The first order population moment expectation of x or mu 1 dash is equal to capital N into p. The second order population moment mu 2 dash is equal to NP into 1 minus p plus n square p square. Here we have two parameters n and p. So, we need two equations to solve or to find out the moment estimators of n and p. So, we equate the first order population moment mu 1 dash with the first order sample moment m1 or summation xi by n, and the second order population moment mu 2 dash with the second order sample moment m2 or summation xi square divided by n. Therefore, we get from this one NP is equal to m1, and from this using this equation we get NP into 1 minus p plus n square p square is equal to m2. So, these are the two equations. We have to solve these two equations to get the parameters or the estimators of the parameters of the binomial distribution. Look at these two equations here. Let us call this as equation number 1 and this as equation number 2. From the first equation we get p is equal to m1 by capital N. Now, expanding the second equation we have NP minus NP square plus n square p square is equal to m2. Now, we can see that in the first equation NP is equal to m1. So, let us replace NP by m1, hence we get m1 minus this is NP square. So, m1 into p plus this is n square p square. So, it is m1 square is equal to m2. Now, we have there is only one parameter p and hence we get m1p is equal to m1 plus m1 square minus m2 and p is equal to m1 plus m1 square minus m2 divided by m1. These are actually m1 is summation xi divided by n, m1 square means summation xi by n whole square, m2 is summation xi square divided by n divided by m1 is summation xi divided by. We can see that now the p is a function of the sample values. Therefore, the moment estimator of p is p curl is equal to summation capital Xi divided by n plus summation capital Xi divided by n whole square minus summation capital Xi square divided by n whole divided by summation Xi divided by n. Now, we have one more parameter capital N, and from the first equation we have m1 is equal to np. Therefore, what is n? N curl is equal to m1 divided by p or p curl. Hence, we got the moment estimators of the parameters of the binomial distribution. Now, we have uniform distribution. So, we are taking a random sample from the uniform distribution. We consider uniform distribution with parameters a and b, where a and b are real values. In this case, we have the density function is f of x a b is equal to 1 by b minus a if a less than x less than b. The first order population moment, again we have mu 1 dash or expectation of x is equal to a plus b divided by 2, and the second order population moment mu 2 dash is equal to a square plus b square plus ab divided by 3. Here we have two parameters a and b. So, we need two equations, hence equating the population moment mu 1 dash with the sample moment m1, we get the first equation as a plus b by 2 is equal to m1, and the second equation as m2, or we can write it as a square plus b square plus ab by 3 is equal to m2. So, these are the two equations. Solving these two equations, we will get the values of a and b, or the estimators of the parameters a and b. So, to solve this equation, let us take a plus b as 2m1. From this we get b is equal to 2m1 minus a. Substituting the value of b is equal to 2m1 minus a in this equation, we get a square plus 2m1 minus a whole square plus a into 2m1 minus a divided by 3 is equal to m2, that means it is equal to 3m2. Now, expanding we get a square plus 2m1 whole square, that is 4m1 square plus a square minus 4m1 into a plus 2m1a minus a square is equal to 3m2. This means a square plus a square minus a square. So, we have a square plus minus 4m1a plus 2m1a. So, it is minus 2m1a plus 4m1 square minus 3m2 is equal to 0. Here you can see that it is a quadratic equation in A. To solve for A, we get A is equal to minus, so this is of the form ax square plus bx plus c is equal to 0. So, solving that we get A is equal to minus b, that is 2m1 plus or minus square root of 2m1 all square minus 4 into, here the coefficient is 1, minus 4 into 4m1 square minus 3m2 divided by 2. So, this is the moment estimator of the parameter A. Now, substituting for B or substituting for the solution of B, we have B is equal to, from this equation, B curl is equal to, this is our A curl. So, B curl is 2 m1 minus A curl. Depending on the sign of A and B, we can propose the estimators as given here. So, we got the moment estimators of the parameters of the uniform distribution, where A and B are the parameters. Now, let us consider another example. That means, you are taking a random sample from the normal distribution n mu sigma square. So, here also the first order moment population mean is mu 1 dash is equal to mu, and the second order moment mu 2 dash is equal to sigma square plus mu square. Here there are two parameters, so we need two equations. Therefore, equating the first one with the first order sample moment, we get m1 is equal to mu. That means, the moment estimator of mu is mu curl is equal to m1, and the second equation we have m2 is equal to second order sample moment is equal to second order population moment. This is sigma square plus mu square. From this we get sigma square is equal to m2 minus mu square. So, since we have mu curl is equal to m1, this is sigma square is equal to m2 minus mu curl square. Now, let us consider a random sample from the gamma distribution with parameters m and p. The density function of gamma distribution is f of x m p is equal to m raised to p by divided by gamma p e raised to minus m x x raised to p minus 1, where x is greater than 0. Then the first order moment expectation of x is equal to p by m. If you do not remember the first order population moment or the expression for the first order population moment, you can find out it using the expression expectation of x is equal to integral over x into f of x m p dx. So, this is expectation of x, and expectation of x square, this is equal to p into p plus 1 divided by m square. So, this is mu 1 dash, this is mu 2 dash. Here we have two parameters. So, we equate with the first two sample moments. Therefore, we get m1 is equal to mu 1 dash, or summation xi by n is equal to mu 1 dash, and m2 is equal to, or summation xi square by n is equal to mu 2 dash. This is p by m, and this is p into p plus 1 divided by m square. Solving these two equations, we will get the moment estimators of the parameters p and m. Now, this is p square plus p divided by m square. We can write this as, from this equation, p is equal to m into m1. Therefore, p square means m into m1 all square plus p is equal to m into m1. Therefore, it is m into m1 divided by m square. It means that m2 is equal to, here we have m square m1 square plus m1 divided by m square, and that is equal to m1 square plus m1 divided by m. Hence, m is the parameter to be estimated. Therefore, we get m1 by m is equal to m2 minus m1 square, and this implies m is equal to m1 divided by m2 minus m1 square. This means the moment estimator for the parameter m is m curl, it is equal to m1 or summation xi divided by n whole divided by m2, that is summation xi square by n minus summation xi by n whole square. Substituting this value in this equation, that is we have the parameter p to be estimated again. Therefore, from this equation we get, here we have m1 is equal to p by m. Therefore, what is p? P is equal to m into m1, and the estimator for m is m curl. So, m curl into m. So, these are the moment estimators of the parameters m and p. Let us denote it as p curl of the gamma distribution. Now, suppose we have again a uniform distribution, but the parameter is different. Here we are taking a random sample from uniform minus theta theta. So, here we have only one parameter theta, and we know that the first order moment population mean mu 1 dash is equal to 0. But we cannot equate this with the first order sample moment. So, we take the second order moment mu 2 dash, and that is equal to theta square divided by 3. So, in this case we equate the second order population moment, that is mu 2 dash, with the second order sample moment m2 is equal to summation xi square by n. Hence, we get theta square by 3 is equal to summation xi square divided by n, and this means theta square is equal to 3 times summation xi square divided by n, or theta curl is equal to plus or minus root of 3 summation xi square by n. Since theta is greater than 0, the positive value is taken as the estimator. In the case of real data sets, just substitute the values of the sample observations in the corresponding moment estimator to get the estimate or estimated value of the parameter. I shall illustrate it with one situation for your use. Let us consider 15 sample values from the Poisson distribution with the parameter lambda. So, these sample values are 0, 1, 2, 3, 1, 3, 2, 2, 0, 0, 1, 2, 2 and 1. So, we have derived the moment estimator of the parameter of Poisson distribution lambda curl as x bar. So, in this case x bar is summation xi by n, and that is equal to 20 divided by 50. So, this lambda curl moment estimator is 20 divided by 50. We have derived estimators of the parameters of several common distributions in this session, and here we conclude this session on method of moment estimation. Thank you.